Take a physical string, tied down firmly at both ends. When you pluck it, the energy has nowhere to go, so the vibrations are forced to bounce back and forth within those fixed boundaries. When you strike that string with a sharp, sudden impulse, it creates an immediate mess. That single shock instantly fills the space with chaotic, overlapping waves of motion. Calculating exactly what the string is doing at any given microsecond is an overwhelming task. You have to track every point along the length of the string, while simultaneously accounting for how those points move through time. Attempting to track this infinitely shifting reality in physical space is a calculation that quickly exceeds human intuition. Mathematicians describe this chaos using a partial differential equation, or PDE. It's a formula designed to handle systems where multiple variables, like position and time, are all changing at once. This graph illustrates the problem. In physical space, calculating derivatives is incredibly messy because every vector is linked. Solving this PDE is like trying to untangle thousands of knotted wires by pulling them all at once. The tension locks the math into one single knot. To break this knot, mathematicians don't try to pull it apart. They leave the physical reality of space and time behind and shift the problem into an entirely new dimension. This new approach relies on a single rule. Any jagged, complicated motion is actually just a combination of simple, perfectly smooth sine waves stacked together. Because our physical string is tied down at zero on both ends, we use a specific tool to break it down, the Fourier sine series. This sine wave matches our physical limits. It resolves to zero at its start and end points, mirroring a tied-down string. Applying the series, we dismantle that chaotic wave into distinct frequencies, stacked like clean layers. The physical limits of the problem dictate the exact mathematical language we use to dismantle it. We have transitioned out of physical space and time and into the mathematical abstract, frequency space. This is where the rules of the game change. In frequency space, the messy calculus of differentiation becomes simple algebraic multiplication. Because the rules are so much simpler here, the massive interconnected PDE shatters. The result is an infinite family of tiny, independent, ordinary differential equations, one for each frequency mode. The power of the Fourier transform is replacing one impossible interconnected task with a list of incredibly easy isolated ones. We can now solve these independent equations one by one, completely safe from the chaos of the whole system. Because the modes are uncoupled, each one is solved in isolation. What's happening at high frequencies has no impact on the math for the low frequencies. Once the math is finished, we re-emerge from frequency space and bring the answers back into the physical world. By adding these solved modes back together, we perfectly reconstruct the original complicated motion with exact precision. The original interconnected problem was never solved directly. Instead, it was bypassed. The Fourier transform demonstrates a strategy for tackling complexity that applies far beyond wave physics. It illustrates that when a system's natural environment makes a problem unsolvable, the most effective move is to change the environment itself. This chart shows that cycle. Translate the problem into a domain with easier rules, solve the pieces, and translate the answers back to reality. In advanced mathematics, elegance often comes from perspective. Instead of calculating harder, we change